Hello everyone, welcome to my channel AURORABYTE. In the previous class, we discussed about hyperconjugation, application of hyperconjugation. The two more applications are left. Today, I will discuss about them. So, we will discuss about the applications of hyperconjugation. Application of hyperconjugation. The fifth point is dipole moment. Dipole moment. Let us consider two molecules like this and this. Now, if we want to distribute the charges, we can write this like this O minus and C plus. Similarly, for this compound, it is also O minus and C plus. Now, if we want to compare the dipole moments of these two compounds, so A and B, the dipole moment of B, it's higher, more dipole moment. So if we want to compare this, we will discuss the hyperconjugation effect of hyperconjugation. So in this case, the alpha hydrogens are present and they take part to a hyperconjugation and stabilize the carbocation so that this structure is more stable, and obviously this has more dipole moment. This is the next point is mm, electron density in the ring. Electron density in the ring. Now let us consider three compounds like this: benzene, CH3, and only benzene and benzene ring with CCl3. So in the first compound, uh, we can see the alpha hydrogens are present. So it will show the hyperconjugation, that means plus H, positive hyperconjugation, and increase the electron density of the ring. And in the middle, the only benzene, there is no hyperconjugation. No hyperconjugation, no alpha hydrogens. And in another case, we will see the negative hyperconjugation here, minus H effect, negative hyperconjugation. It decreases the electron density of the ring. So if we want to compare this, so the first one is more electron density. Electron density of the in ring, if we consider the order and take this is more A, B or C. So A is greater than B is greater than C. Now the next topic is resonance. So what is resonance? Resonance basically is delocalization. It's a delocalization, or we can say conjugation. relocalization of conjugation of electrons. Which kind of electrons? Obviously, it's not the sigma electron, it is pi electron. So these pi electrons are of two types. One is lone pair, and another is anion. Now, this lone pair or anions are of two types. Lone pair or anion are of two types. One is localized and another is delocalized. Localized means fixed or rigid, and delocalized means movable electrons, easily movable. Now, let us consider some examples. Examples like we consider a compound like this. Here, the lone pair on the nitrogen atom, it it is actually delocalized because it can take part in conjugation like this, and we get the equivalent structure like this. So this lone pair is movable. Position, it changes its position. It is movable, that is delocalized. Now another example is like this. Now this lone pair is not movable because there is no scope for further conjugation. This kind of shifting is not possible. This lone pair is fixed. That is, it is localized. Now the next example is pyridine. This is pyridine. This nitrogen lone pair is also fixed because there is no option for further conjugation. Here is double bond, and in the another side there is single bond, but actually the three double bonds are in resonance with each other. In this way, so we can say the equivalent structure like this. The electron cloud is present in the ring, so this lone pair is fixed. It can't be uh, conjugated, so this is localized. Now another structure is like this is the bridged structure. So this lone pair is not movable, this is localized. Why? Because if we shift these lone pairs here, we get a double bond. Here, a double bond. Now, this structure is very unstable, most unstable, because the double bond in bridgehead position, double bond in bridgehead position, this is most unstable. It does not obey the Bread's rule. It doesn't. It is most unstable. It does not obey the Bread's rule. Actually, it doesn't obey. No, it according to Bread's rule, it is most unstable. Double bond in bridgehead position or cation or any charge in the bridgehead position, it's very unstable according to Bread's rule. Now the next example is like this. The lone pair on the oxygen atom, it is also localized because there is no further conjugation. It is localized. The next example is benzene ring and negative charge. This is also localized. It is similar to PDD. And here is no option for conjugation. Now the next example is this CH2 NH2, CH2 minus NH plus. So here it is also localized. It is most important exception actually. So it is like to be shifted here the negative charge and neutralize the positive charge, but this will not happen. Why? Because this nitrogen atom, it doesn't have any empty orbital. It's no empty p or d orbital. P or d orbital. So this is localized. Now the next topic is linear conjugation or cross conjugation. Linear conjugation and or cross conjugation. Now let us consider a compound like this. So the conjugation is like this. Now this is called linear conjugation. This is also called one directional conjugation. One directional conjugation. Now let us take another example like this. Here we can see two types of conjugations are possible. One type is this, and the another type is this. Yes. Two types of conjugation, two directions of conjugations are possible. Two types of conjugation is possible. So this is called actually cross conjugation. This is called cross conjugation. Cross conjugation. So the stability order is linear conjugation. Linear conjugation is always stable than cross conjugation. Is always stable than cross conjugation. Cross conjugation. This is very important actually. Linear conjugation is always stable than cross conjugation. Now the next topic is resonating structure and their stability. Resonating structure and their stability. Let us consider a compound is phenol. Now we draw the resonating structures of this, all possible resonating structures. The lone pair of oxygen, it shifts like the lone pair of oxygen, it shifts like this, and this, the double one, shifts here, and we get the structure like this kind of structure. one negative charge on the carbon atom and positive charge on the oxygen atom. Now, after further conjugation, it looks like again it looks like this after further conjugation. Again, the conjugation is like this and the structure is like this. And lastly, again this conjugation and we get the previous structure, the neutral structure, the original structure. So these are the resonating structures of phenol. 1, 2, 3, 4, 5. These are also called canonical structures. So how to compare their stability? To compare their stability, there are some rules. We will discuss the rule for stability of resonating structures. So what are the rules? Firstly, octet fill-up. The octet complete compounds are more stable. Octet completed forms are more stable. Octet complete, more stable. Secondly, the neutral structure is more stable than charged structure. Neutral structures are more stable than charged structures. Thirdly, the localization of charge. Localization of charge. That means negative charge, charge. That means negative charge on the more electronegative atom is more stable. Negative charge on the more electronegative atom is more stable and vice versa also. Positive charge on more electropositive atom is more stable. Fourthly, separation of charges. Separation of charges. That means opposite charges should be close. Opposite charges should be closed. That structure is more stable. So now if we want to consider the stability order of the previous example, so we will follow these rules actually. Now let us see what happens for this example. If we consider the stability order, the stability. So you can see for the first and the fifth compound, the first and the fifth form, these are neutral form and also octet is completed. So these are the more stable forms. 1 is equal to 5. Then the second and fourth form, the opposite charges are very close to each other. So these are more stable. So we can say 2 is equal to 4. Then lastly, the third structure, the charges are very far away from each other. So these are the stability order. Now another example like this compound. If we draw the canonical structure of this compound, we get this. So now the stability order A and B, the stability order, it is A greater than B. Why it is A greater than B? We consider here the octet rule. For the A conform, the oxygen atom has 2, 4, 6, and 8 electrons. So octet pillar, octet pillar. But for the next form, this carbon atom has 6 electrons, so this octet is not pillar. So the stability order is A greater than B. Now the next example is like this. Now if we want to draw the canonical structures of this, like that phenol, so similarly the lone pair of high nitrogen atom shifts here and we get the structure like this. Again shifting and we get like this. Actually, I missed one double bond actually. One double bond is here and another is here. Okay, I'm sorry. So now the further conjugation is like this. Yes. Now we get the structure. This is the structure. Then further conjugation. Now again further conjugation and here we get the original structure, the neutral structure. Here is the neutral structure. And actually then these neutral structures are the most stable form as like previously discussed. So here is the neutral structure. Now if we want to compare the stability A, B, C, D, E, F, the stability order, stability, it is obviously A equal to F. These are most stable. Then the C and D, the charge separations are small. The distance between charges are small. So C is equal to D. And then B and E, the charges are far away from each other. B and D. So this is the stability order. B and E actually. So that is it for today. We will discuss about types of resonance, applications of resonance in the next class. So thank you for watching. If you like this video, please press the like button. If you have any doubts, put in the comment section. And if you are new to my channel, please subscribe the channel. Thank you. Thanks for watching.